This lesson is a continuation of section 3.4, solve equations with variables on both sides, or again, VOBS as I say, VOBS, my abbreviation for variables on both sides, a VOBS problem. There's just one more thing in this section I do want to show, that's why it is taking a few lessons to do this, but there's something interesting that can happen that I want to show us when we have a problem with variables on both sides. There are a couple special cases or things we have to keep an eye on or keep an eye out for that could happen if I'm solving one of these types of multi-step problems where I have a variable on both sides. First, I'm just going to start off with one of our examples like we've seen in the past couple lessons. So 51 minus 7t equals 10t. Again, when you're doing a problem like this, you should follow your steps. Distribute when you can. Collect like terms when you can. Can't do either of those, then we're just down to step 3. Get the variable on one side. So again, what I think about or what I tell students to think about is trying to eliminate the variable from one side. That'll put the variable all on the other side. So if it's 51 minus 7t, I'm going to add 7t, and I do that to both sides. How does it help me on the left side here? If I have negative 7t plus 7t, well, if I add those together or combine those terms, that'd be like 0t, so there'd be none of them. So that'd be all gone. So again, that helps me in terms of it eliminates the t's on the one side. Now I just have 51 on the left side. 10t plus 7t gives me 17t. And then now I'm down to just one step in this particular problem. Divide by 17 on both sides, so t equals 3. So there's what it's been looking like when we solved a problem that has a variable on both sides of it. But today I'm going to show you some special cases. There are some kind of different things that can happen sometimes, though, when I'm doing these problems. And so there's some kind of things that we have to keep an eye out for, be on the lookout for, because there's some kind of, you could say, weird cases, but things that as long as we know, can recognize them, they're not too tricky to deal with. So this problem right here that I've got on the board is an example of one of these special cases that I'm referring to. And again, special cases I'm just saying because it's just different than some of the answers we can usually get. And so, but as you'll see here, I'll talk about what it means or what I mean by special case as you see what the answer or what it shows us. Again, just like a normal problem though, it might say solve. Again, what does solve mean? It finds out what value of x would make this equation true. What could I put in for here and here that when I put that number in, times it by 2, and add 3 on this side, will give me the same number as when I multiply by 2 and add 5 on that side. And right away, maybe as you look at this problem, you might notice something kind of fishy going on here. But what I'm just going to do for now is I'll just kind of pretend like I'm going through my usual solving steps. And all of a sudden, we'll run into maybe the issue. So again, maybe I would think about my steps and say, okay, step number 1. Can I distribute anywhere? No, I can't distribute anywhere. Can I collect like terms on either sides? No, I can't do that. So I'm on step 3. Get the variable on one side. Well, what I try to tell you, what I tell many students, is try to eliminate the variables from one side, and that'll get them all on the other. So let's say that I'm just in particular looking at this left side, and I'm going to say, well, I'm going to eliminate the x's from this side. What would I do? I'd subtract 2x from this side. Whatever I do to one side, I have to do to the other side, so I need to subtract 2x from the other side as well. When I subtract it from this left side, 2x minus 2x, I know just gives me, no more x's. They're just gone. So all that's left on this side is 3. When I look at the other side, 2x minus 2x, well, that also gives me 0x. So essentially, these just go. And all I have left is 5. So all I'm left with, or what happens in one of these special cases, what will often happen, and these can happen when I have a VOBS problem, when I have a variables on both sides problem, is there may be a time when I try to get all the variables on one side, and by doing that, I actually cancel out all the variables, and all that's left is some kind of statement here. 3 equals 5. So first of all, I'm just going to bring it over here. If you look at 3 equals 5, that's not even true. I'd have to put a slash to the equal sign. And when you're doing these problems, that's what I want you to do. Slash to the equal sign. That doesn't make sense. What is going on here? Well, again, I'm going to bring back to the original problem. Take a look at here. And again, we're trying to find out what x is, but when no x's are in the problem anymore, it makes it kind of difficult to figure out what x is. Look back at the original problem and see what it's trying to tell us. Again, like I kind of talked about right at the very beginning, maybe you caught on, but you're going to take some number and multiply by 2, and you're going to add 3 to it. So think about a number like that. You're going to take some number and multiply by 2, and then you add 5 to it. And the equal sign said these problems, or these two numbers, have to be the exact same. If you think about that for a little longer, you're going to realize that there's no way that can happen. I can't take some number, multiply by 2, and add 3 to it, and take the same number, multiply by 2, and add 5 to it, and get the same answer. Like, there's no way that can happen. The one on the right side is always going to be whatever I get on this right side, it's always going to be 2 greater than whatever is on the left side. So there's no way that could ever happen. What happens here in this case, again, remember what solve means. Solve means that we're trying to find out what x is. Well, if I get something like this in a problem, though, where I get down to a statement that's not even true, we call that a no solution case. And again, this is something I would like you to write down in your notes if you're copying notes along with this. This is a no solution case, because what we're saying is there's no answer. Usually we get an answer like x equals 7 or x equals -2. But in this case, we didn't get anything like that. So what happens is we get down to this situation right here. 3 does not equal 5. And I just write, once you see something like that where you end up with a statement that's not true, that means this is a no solution case, and you write no solution. There's no number that will make that top equation true. Again, just like we were talking about. If I take some number multiplied by 2, add 3, I can't take that same number multiplied by 2 and add 5 and get the same answer. I'll even make a simpler one down here. I'm going to say x take some number and add 2 to it, and that's got to be the same as taking some number and adding 5 to it. There's no way that this equation will ever have any kind of answer to it. There's no number I can put in here and put in here, and then the equation will say that they're the same. Like there's no solution for that. And again, same thing with this one. If I would just start solving this like a normal equation, let's say I'm going to eliminate the x's on one side, I eliminate them on the other. When I cancel them out, what am I left with? I'm left with just 2 equals 5, again, which is not a true statement. So you put a slash through it, and again, this would tell you that this is a no solutions case. When you're left with no variables, you've canceled out all your variables, and you're left with a statement that's not true at all, that means there's no solution for it. There's no possible number you could plug into that original problem where you would get an answer. There's no number you can add 2 to and add 5 to and have the same exact answer. So this is why this is one of those special cases I call them. This is the no solution case. So one to keep an eye on. On that first page, we had the special case where there's no solution. So that's one thing that can happen. There's one other special case I want to talk about. I'm going to look at this particular problem to showcase it. And again, as you look at this problem right away, you might see something kind of funny, but we'll talk about what to do in a second here. I'm going to start solving this problem. It says 2x plus 1 equals 2x plus 1. Again, already maybe you're starting to see something, but let's start solving it just like we usually would and just say that we haven't noticed that yet, what we're going to see here in a second. So again, if I'm going to solve this problem, I can't distribute anywhere, I can't collect like terms, but I'm going to try to get all the x's on one side. Let's subtract 2x from both sides. When I do that, it eliminates the 2x's from here, from the left side, so all I have left is on the left side is 1. If I subtract 2x on the right side, they also cancel, and all I have left on the other side is 1. So all I'm left with is 1 equals 1. Again, just kind of bringing it over here. This is what I have. And is that true? Well, yeah, 1 is equal to 1. So you'd put a check next to it and say, yeah, that does work out. Well, what's going on in this particular problem then? Because again, there's the variables on both sides of Bob's problem. And all of a sudden, when I started solving, my variables canceled out. But this time, remember on the previous page, we ended up with like 3 equals 5. And again, that's not true. We end up with something like this. That's not true. That was the no solutions case. Well, what happens then when I end up with something that is true? What happens if I end up with 1 equals 1? That is, 1 is the same as 1, so that does work. Well, again, look back at the problem and notice, what is it telling us? It's saying take some number, multiply it by 2, and add 1. And that's going to be the same as if you take the same number, multiply by 2, and add 1 again. I can't think of a number that won't happen for. Every time I take the same number, multiply by 2, and add 1, I'm just going to get the same thing if I, for some reason, did it again. So that's always going to work. So you could think of what happens in this case is that you could almost think of there's 2 ways. They have a different word for it, but you can think of that it's all real numbers. Like any possible number you could think of as an answer. And I've seen that abbreviation used for this. All real numbers. So this means that any number you can think of is an answer. All real numbers. You can put that for a solution. It's just this abbreviation right here. Otherwise, the book also talks about this. It's called an identity, as they describe it. And again, it means the same thing, though. They're saying any number will work for the solution. So they're just saying no matter what number you plugged in for this equation, it would give you the correct answer. Again, just kind of making another simple one down here. Let's say I had x. I just say, oops, x plus 2 equals x plus 2. Okay. Again, no matter what number I would plug in there, I would get that answer. So you could either put, I would be accepting of either of these two things because you will see these different types of answers. You could put identity. And why do they use identity? Because I think it's just saying, I would describe it as almost like looking in a mirror, like you see the same thing on this side as you do on this side. It keeps the same identity, no matter what side of the equation it's on. So you could think of it like that. Or again, I've seen the abbreviation. Again, all we know right now is real numbers, so we'll stick with that. All real numbers. That abbreviation, the R, kind of like a double-lined R. Again, just kind of showing again how I make it. I make a line, then I make another line, and then I kind of make an R with it. That means all real numbers. That means any number will be a solution to this problem. Again, this is one of those special cases that we'll run into. Sometimes we can run into the case where there's no solution, or we can run into this case where there's all solutions. All real numbers are a solution. I've got just two more examples here, again, just to showcase the special cases that we've talked about today. And obviously, I've kind of set it up so one of them is going to be a no solutions case, and one of them is going to be an identity or all real numbers. So we'll see if we can pick out which one is which here as we solve each one of these problems. So we'll start with number 1 here. Again, I would start solving this problem just like you would any other problem. Again, what I'm telling you about these special cases is that you don't necessarily have to see them right away in the problem. I've told you the steps to solve any type of multi-step equation. You just follow the steps like you've always done, like you've done the whole chapter. And all of a sudden, if you run into one of these special cases, I mean, you'll be able to tell by the end because you'll have no variables left in your problem, and all you'll have left is a statement like 2 is equal to 5, which isn't true. Or maybe you'll have 7 is equal to 7, which is true, and then you'll know it's one of those special cases. It's when the variables cancel out. But again, you don't have to be aware of it right away in the problem. You don't have to be able to look at problem number 1 and say, oh, that's a special case. If you don't know that yet, that's okay. You just start following the steps like you normally would. You'd say, can I distribute? Nope. Can I collect like terms in this problem? Nope. All right, well, now I'm going to get the variable on one side by itself, and then start getting it by itself. So you'd say, oh, I'm going to eliminate the variables from the left side, let's say. Subtract 3x, subtract 3x. I have to do the same thing to both sides of the equation. When I do that to the left side, 3x minus 3x gives me no more x's. They're gone. All I have left is 10. Okay, that's what I wanted. I wanted to eliminate them from the left side, but when I eliminate them or I subtract from the right side, I also eliminate over here. I also eliminate on the right side too, so they're gone there. And all I have left is 10 equals negative 5. 10 on the left side, negative 5 on the right side. Well, again, I'm left with all the variables are gone. And so this is one of the special cases here. I'm looking at that statement. That's not true. 10 is not equal to negative 5. So I put a little slash to the equal sign, and when I think about my two special cases, this is the one where there's no solution. No number will work. There's no value for x I could plug in for that original problem and make the equation true. So this is what you'd write for the answer. You put a slash through that equal sign once you get down to that final statement, because it's not true, and then you write the words no solution. Well, then knowing that, kind of gone through problem 1, kind of told you we'd have one of each case here. We'll just look at problem number 2 here quickly. Again, if I'm going through my steps, I'd say, well, step number 1, can I distribute anywhere? Nope, I can't do that. Step number 2, can I collect like terms? Yes, I can actually on this left side. On the left side, I can take 3x plus x. 3x plus essentially one more x, so give me 4x minus 8. So now I have 4x minus 8 on the left side. I have 4x minus 8 on the right side. Again, maybe you kind of noticed something. I've done my collect like terms now. Now I'm going to try to get the variables on one side. I could think about eliminating them from the left side, so I subtract 4x. I'll do that to this side too, the right side. And what do you know, on both sides they end up canceling out. And all I'm left with now at this point, since I've canceled all my variables, I'm left with negative 8 equals negative 8. Again, as I look at that, that is true. That is, in this case, that is true. Negative 8 does equal negative 8. It's the same number. So again, you could put identity with this or write that as an answer. Or as I'll talk about in class, I'll also accept this. This means all real numbers are a solution to that problem. I could plug any number. I could plug any number back into this original equation, and I'll get the same thing on the left side as I would get on the right side, no matter what the problem, what the number is. And again, you'll be able to find these special cases. Don't feel like you have to know them right away as you look at the problem. You just follow the normal steps. And when you get to one of these two situations where the variables are out, all gone in the problem, that's when I'll be able to tell if I've run into one of those special cases. And again, we can tell which each one is. No solution is when I get something that's not true. Okay, the 10 does not equal -5. Identity or all real numbers, that's when I get something that is true at the end. So again, now we can recognize those special cases. They will come up from time to time in the problems as we go on this year as well.